Alright, this is Mr. Craig, hopefully with part 3 and the final part here. I want to show a virtual titration here real quick just to show how close we get to getting a pH of 4.23. Again, we're using a 5% rule, so I would hope that we get very, very close. In this demo here, I've got acetic acid, which is right here, and I've got my concentration. Things are a little bit scrunched up here. And I've got an exact concentration and an exact amount here. And then I'm going to use my sodium hydroxide, which I have my concentration of 0.2 and 50 milliliters. And then we need to use an appropriate indicator. And since we want our pH, when we get to the equivalence point, to be something else, the indicator really doesn't have any bearing on what we're doing at this moment here. So we'll pass on that for a moment. And then here's our burette, which is filled up with our sodium hydroxide within our Erlenmeyer flask here. We have our acetic acid, our 25 milliliters of that, and you'll notice that we start off with a pH of 2.76, which is pretty cool because that's what we calculated at the end of part B. Our pH was at 2.76, so we start off on a good note right off the bat here. Okay, and what's going to happen is once we start the titration here, you'll notice here that we have our initial volume, and that is of the sodium hydroxide within the burette. Current volume, since I haven't used any, is still 50, and then the amount of solution used. So what I want to do is try to go not too fast here and start titrating. So you'll see that we can see that the amount is being introduced into the Erlenmeyer flask, and as expected the pH is going up. Now I'm going to slow it down once we get very close to the 5 milliliters here. Let it run here. And we can go real fast or we can go real slow, so I don't want to go too fast here. Alright, so we're at 4. So I want to slow this baby down just a bit here. Okay, so, and the pH is increasing steadily. Hopefully this will get right at exactly 5 when we get there. Okay, we're 4.6 here. 7. Okay, I'm going to try to slower down here, 4.8, and about right there. Okay, 4.9, 4.99, and it says that our pH is 4.2. Even though our calculation says 4.23, that's pretty good considering that we've been using the 5% rule here. Also, we'll take a look at the titration curve as we go along, so we're not even close to the half equivalence point here, which is kind of neat. We'll come back to that here in a moment. Alright, so continuing on with the next part here. Okay. Part D says calculate the pH at the equivalence point of the titration, part C. So remember, at the equivalence point, the moles of the weak acid is equal to the moles of the strong base. The information that was given earlier, again, our moles of the acetic acid, like we said earlier, isn't changing throughout the whole problem. So at the equivalence point, if we have 0.00429 moles of acetic acid, then we are going to need the same exact number of moles of the sodium hydroxide. So one way that we're going to need to find out how much of the total volume of the sodium hydroxide added is to do a calculation. And in this case here, since we know the number of moles, 0.00429 moles of sodium hydroxide, and we know the concentration, we have to start with the number of moles so that the moles will cancel out, and then we'll be left with our volume, which in this case is our milliliters. So to have 0.00429 moles of the strong base added, I'm going to need 21.45 milliliters of sodium hydroxide added to the 25 milliliters of the acetic acid to reach the equivalence point. Now again, using our ice chart here, same format, we're going to start off with approximately 0. So this is acting like we're starting from a brand new titration. We're not going to have anything originally here, so we're going to start with just 25 milliliters in the Erlenmeyer flask, and then we're going to dump the 21.45 milliliters of the sodium hydroxide in there. So at the equivalence point, we're going to have the same number of moles of the acetic acid, same number of moles of the hydroxide. So both of these will go to exactly 0. and then equilibrium is going to be reestablished. So we're going to have the reduction of 0.00429 moles on the product side, but we're going to have the addition on the reactant side. So we only have a known constant or known mole amount for the common ion or the acetate. Alright, so we need to find out what the concentration of the acetate ion is so that we can find the pH, or actually the pOH, of the hydroxide. Before we can do that, we have to know what the total volume of our mixture is. So we know that we have 25 milliliters of our acetic acid, which is not going to change throughout this reaction, and then the 21.45 milliliters of the sodium hydroxide for a total volume of 46.45 milliliters. Convert that 46.45 milliliters into liters so that we can get our new concentration. Now, in this ice chart, you'll notice that I have Y's in here. Now, I don't want you getting hung up and going, well, why are you using a Y now instead of an X? Well, it's just different, so it's okay. You use whatever variables you like. However, we're still going to use the 5% rule. And we're also still going to use the same Kb value that we found in part C. So this part here I just stuck in there to remind you that we're still using the Kb since we have hydroxide. Use your expression. In this case here, we do not know the concentration of the hydroxide. We do not know the concentration of the acetic acid, but we do know the concentration of the acetate ion. Rearrange the variables here, and that Kb should say 5.5 times 10 to the negative 10. Excuse my error on that. We're going to solve for Y by using the 5% rule again. So get rid of the minus X and solve for Y. So now Y squared is equal to all of this. And then what we're going to do is we're going to take the square root of Y and get our concentration of hydroxide, also the concentration of acetic acid, but again, you can't find the pH from an acid. You have to find it from either hydrogen or hydroxide. So here's our concentration at the equivalence point. Let's quickly go to the demo. Now we already have 5 mils added in. Let's continue on here and add our 21.45. So I'm going pretty quickly here, and let's stop it for a moment here with 11 mils. And I want you to see that the pH has gone up a little bit. We're actually moving along on our titration curve here, so we'll keep adding our titrant here, which is our sodium hydroxide. Notice the pH is still slowly rising. As we get closer, I want to slow that down a little bit. Okay, so 18.9 there. Okay, so again, we're trying to get to 21.45, and notice that the pH will start taking off here. We have to be beyond our half equivalence point here, so it's right about there is our half equivalence point. So we'll continue on, and shortly you're going to start to notice the pH is going to start to change a little more quickly. So there's 19.7, okay, almost to 20 here, and 5.9, and we're still increasing. Alright, now we're getting to that 21. So let me stop it right about here. Take a look. Now we start to see that that curve is starting to go upward. That means we're very, very close to our equivalence point. So 21.45. And stop. Oh. Now that's kind of a pinkish color there. 21.45. If I go another drop there, it's going to really turn dark red. Boom. 21.45. So 9.8. Now let's look at our titration curve here, and let's finish this off real quickly. And you'll notice that the pH really peaks out there. Alright, so now we have our pH here where we want it around 8.86. Check the video real quick to see if we got close. We're running out of time.